Okay, everyone, let's do this question from module 3 for that Cape Physics Unit 2 exam from June 2018. Okay, so this question is about the photoelectric effect or this phenomenon of photoelectric emission. So they're asking us to describe that phenomenon, like what is that all about when there's photoelectric emission? And that's really when the surface of a metal is illuminated with electromagnetic radiation, and then the electrons are then emitted from the surface of that metal, right? There's a frequency of electromagnetic radiation that's associated with that light that it's being illuminated with, and that has to be above a certain value, right? So we've captured all of that here. Then they're asking us to define each of the following quantities that are associated with photoelectric emission and state each unit of measurement, right? So first we have the work function. And what the work function is that is the minimum amount of energy that's needed to free the electron from the surface of the metal. And that has units of joules, right? Because that's a work, right? So units of joules is what we use for work function. Now, the cutoff wavelength, this is the maximum wavelength of the incident electromagnetic radiation that's required for electrons to be emitted, right? So that's just a max wavelength of that incident electromagnetic radiation. And so, of course, our wavelength is going to have units of meters, right? So that's just meters in M, right? Okay. So moving right along, they're telling us for part C, that light of wavelength lambda, right, is incident on a polished metal surface. And they're saying that we should derive an expression for the maximum speed of the photoelectrons ejected, right? So now this is where it's important to know some of the theory behind how photoelectric emission actually works, right? So for the photoelectrons to be ejected, or for those electrons to be ejected from the surface of that metal, the energy of the photon, right, has to be greater than that work function, which is denoted as phi, right? So the energy of the photon, which is given by E is equal to HF, and can be simplified further as H times C over lambda, right? This is just a substitution for the value of F here. This energy has to be greater than our work function, which you might remember is the minimum amount of energy that's required for those electrons to be ejected, right? Okay, so in the case now where we have the energy of the photon or that incident radiation, if that energy is greater than the work function, then the electrons ejected move with kinetic energy. EK is equal to half m v max squared. So that's your maximum speed, right? That the electrons are going to move off with, right? So we can represent that mathematically by this formula up here, which says that, you know, if we have more, if our energy, right, is greater than the work function, then we're going to have some leftover, right? And that leftover energy is what's then converts to kinetic energy. And that's then translated to the speed with which those photoelectrons will be ejected, right? So again, we can just plug in what our formula was for that energy of the photon, which we had from here. So we just plug that in here. And of course, phi is our work function. So we put that there. And then of course, that's whatever the residual energy is will be half mv max squared, right? So all we have to do at this point is just rearrange this formula, making v max the subject. So to do that, we multiply all of these by 2 and then divide by m, right? Which is the mass of our electron, and then just square root everything to get the value for V max, right? So this is going to be our expression for maximum speed of photoelectrons ejected, right? And we have that, of course, in terms of our lambda or wavelength that they gave us, right? So this is the expression that they're looking for here for 4 marks. And then moving right along, they're asking us now to calculate the maximum speed of the ejected photoelectron when lambda, now they're giving us a value for this lambda, when lambda is equal to 100 nanometers, right? If the metal is thin and it has a work function of 5.5 electron volts, right? Okay, so we're going to use our formula that we derived in part 1. And so this is this formula here. And we're just going to substitute in the values here. We know that H is Planck's constant, so we put that here. We know that C is the speed of light. And then our lambda, they gave us in nanometers. We're going to convert that to meters. So that's what we did here. Then we're going to subtract our work function, which is 5.5 electron volts. But to keep everything in SI units, we're going to just multiply that by 1.6 times 10 to the negative 19, which is what? The equivalent of 1 electron volt, right? So we multiply that by 5.5 since it told us that the work function is 5.5 eV. So now we have our value of work function in joules here, right? And per this formula, we're going to just multiply everything in the top by 2. So this is my times 2 here. And then finally, divide that by the mass of an electron, which is 9.1 times 10 to the negative 31. And then find the square root of all of that. And when we do that, we come up with this Vmax, right, of 1.56 times 10 to the 6 meters per second, right? So that's all they're asking us to do is just apply this expression that we derived in part 1 and plug in the necessary values to get out our Vmax, right? But the key thing here is that you have to make sure that your units are consistent, that they are in fact in SI units, so that your Vmax will work out in the units of speed, okay? So that's all, guys. That's all they wanted for this one. So again, this is module 3. Particularly on the photoelectric effect or photoelectric emission. And this is from the June 2018 paper, okay? All right, see you on the next video.